Okay, so this is the 23rd lecture, and the title are the singular values and the SVD, the singular value decomposition for linear maps. Okay, so before we start our lecture, we will need the following four results. Okay, so for any t linear linear map from V to W, t adjoint t is a positive operator on t, and also the kernel of t star t is equal to kernel of t, and the range is equal to the range of t star. And the rank for t, t star, and t star t are all the same. So let's just prove A first. So we first know that it is an operator on V, so we just need to verify that it is positive. To verify it is positive, we have to first verify it is self-adjoint, but this is trivial. So now let's verify the positivity of this operator t star t. So t star t v, right, gives you this, and you can move it to there, gives you norm squared, right? So it's a positive operator. Okay, now for part B, well, if v is in kernel t star t, then this will be equal to this, right, by above, right? I mean, this, right? They're the same, right? They're the same. So if v is in kernel of this, so this will be 0, which means that tv is 0. Conversely, if v is in kernel of t, if v is in kernel of t, then t star tv gives you this, which is 0. Yeah. Sorry, 0 and w, right? So for part C, we want to show that is the range of t star. And because t star t is self-adjoint, so by previous proven statements, we have the range of t star t equals to kernel of t star t perp. And this is equal to ker t perp, right? And ker t perp is equal to range t star. All right. And for part D, we want to show that all their rank are the same, right? The rank are all the same. Well, for this to the end, rank of t, right, is the rank of t is equal to ker t star perp, right? So the dimension in terms of dimensions, right, is equal to this. And for this ker t star, we have the orthogonal complement, right, which is dimension of v minus the nullity of t star, right? And this by the fundamental, the dimension theorem, right, this will be equal to rank of t star, right? Null t plus rank t star gives you dimension t. And rank of t star, proven before, it is equal to rank t star t. So this equal to this equal to this. Okay, so this is what we need so far, and now let's start our lecture. So first, for any linear map t from V to W, because t star t is positive, right? This is star, right? T star t is positive, so it is self-adjoint. So we can apply the spectral theorem. There exists psi n orthonormal basis v, and lambda 1 lambda n non-negative because it's positive. If it's positive, then eigenvalues are non-negative, right? So such that we can just reorder it, and we have t star t of psi I equals to lambda I psi I for all the i's. Okay, and now we define the list of the square roots of them. The list of all the square roots of them are called the singular values of t, and we count the repetitions. So this is not a set with curly braces, it is a list, right? So 3, 3, 2, 0, right, is the singular values of t, or the singular values of t. So the theorem states that, okay, if t is injective, if and only if 0 is not in a singular value, and the number of positive singular values is equal to rank of t. And t is surjective if only if the number of positive singular values is equal to dimension of v, because it's rank T is equal to time B, so B implies C. So we just need to show A and B. And if T is injective, if only if 0 is not a singular value of T. We know that this works even if we replace the word singular by eigen, right? Yeah. So by part A, we have cur T equals to cur T star T, so we're done. Right, if we just work with T star T by our framework from here, right? If all of them are like positive, then them are positive, right? So with the O and B, right, they're all positive, so yeah. 0 not a single, so then 0 is not an eigenvalue for T star T, right? But the kernel of T star T is equal to kernel of T. And for part B, we want to show that the number of positive singular values is equal to the rank of T. So let M be the number of positive singular values. If none of them, then range of T will be equal to 0W, right? So rank T will be equal to 0. Now, if M is between 1 and N, with the same notation as above, right? When we can pick some of them that are positive and all others is 0. So the range of T star T, we know that it is equal to span of on the basis, right? Yes, this is by a long time ago, but you should be able to know this, right? Because they are the basis, right? So the range is the span of them applying on the basis. And, well, which is precisely the span of those that survived. That is positive, because all others are 0, right? Which is span of those. And this is an independent set. Span of them is independent set. So the rank of this will be just equal to this number M, right, as desired. And now here comes the singular value decomposition. Okay, give an operator and suppose S1, Sm are the positive singular values. Then we have there exists an orthonormal less than V, another orthonormal less than W, such that we can decompose TV into this. So S1, Sm are the singular values, and E1 is orthonormal less than V. The vectors in V, so V and EI is a scalar. So we have a scalar multiplied by a vector in W, right? Scalar multiplied by a vector in W, and this is in W, right? So we have a singular decomposition that looks like this, which we can just by constants multiply A, O, and B. Okay, this is the singular value decomposition, and the proof is okay. Just follow by the definition. So given positive singular value of T, right, we can write S1, Sn as singular values of T. We just fill it out, right? Because some of them might be 0, where N is equal to dimension of V. Right, this is all we did here is just by our framework here, right? It is all what we did here, right? So we fill out the 1, right? Then we have an O and B of V such that is equal to, because the singular values are square roots, right? So we square it back. So T star T EK is S star K EK for K from 1 to N. So from here, we can define SK for the SK that are non-zero, right, from 1 to M, such that TEK SK. Okay, so it's in W, where this is a scalar. This is scalar in R or C, right? Doesn't matter, and this is in W. So this is in W. Then we see that as an orthonormal list, because if for any JK, right, Fj, Fk, their inner product, we have this, right? We don't have to multiply by conjugate here because Sk is what? sk is 0, infinity, right? We don't have to multiply conjugate out. It doesn't matter. And from here, we can swap back to t star t, right? We swap back to t star t, and from here, we apply this here, gives what? S squared ej, right? S squared j, and this power goes away, this cancel out, gives you sj sk, right? And this, we by the ONB, orthogonality of the list of ej, ek, right? This is like equal to this. So we're done. So this is an ONB and sorry, let me just rewrite this. Orthonormal list. It's an orthonormal list in W. Okay. Okay. And now we have for k greater than m, right? This will be equal to 0 because this is equal to 0. Thus, if this is equal to 0, then TEK is 0 because cur T equals to kernel of T star T. If T star T of EK is 0, then T of EK is always 0. Okay, so why we need this? Because we have from here, let's see, TV. For this V, we can decompose it as this. We discussed this a long time ago, right? Because E1, En is the O and B, we can decompose V into this. Now, we use linearity. And because some of them, if k is larger than m, right, this is 0. So the only one that survived are the E1 to EM. And TE1 TEM is equal to what? SKFK, right? So SKFK. So we're done. Here's the decomposition. And here's some comparison between the two important theorems, the spectral theorem and the singular value decomposition. So the spectral theorem describes only self-adjoint operators or normal operators, and it produces a single orthonormal list. And the proofs are different, depends on the field. But for singular value decomposition, although it is by the spectral theorem, right? It describes arbitrary linear maps from inner product space to possibly another inner product space. Produces two orthonormal lists, right? The EIs and the FJs, right? One for the domain space, for the range space. Not necessarily the same, even when the range is like doesn't matter. Like there's no claim on they have to be identical. And the same proof regardless whether the field is equal to R or field is equal to C. Okay? And now we can decompose, given decomposition, the SVD, we can also decompose the adjoint. Now let's see how. To decompose the adjoint, okay, so for TV, right, we just swap EI and FJs, right? And we swap V to W for any W. And this is really the difference here. We just swap them, right? And the proof is simple by direct computation. Given a singular value decomposition, right? From here we just multiply out. Right? Because those are the scalars. So the scalars and F1W, right? F1W plus the scalars here, and FMW inner product. And from here, this is equal to this, right? Because if you go from here, you can reach it back. Okay? It's inner product of V with them. And V with them will be equal to V of T star W. Because we have this, right? These two are the same. So these two are the same. So from here, because this holds for any V and V, right? So you should be able to see that this implies this. Okay, so given an SVD for T, we can also decompose the adjoint, right? And this is everything for this lecture, and I'll see you guys next time. Let's end this with this comparison. Okay, bye-bye.